All right. Hello, everybody. Welcome to Aspen Center for Physics Colloquium. My name is Tao Han from the University of Pittsburgh, and I'm in the program of New Intersections, Neutrino Physics at Crossroads. And fortunately, we overlap with another very exciting program that is New Discoveries in the era of high resolution, low noise CMB experiments. So we are very happy and very lucky to have one of the participants, Colin Hill, to present today's colloquium. Colin got his undergraduate degrees in physics and mathematics from MIT. And he completed his PhD in astrophysics at Princeton University in 2014. He continued on his research and did his postdocs at Columbia University and the Institute for Advanced Study. Currently, Colin is assistant professor in the physics department, Columbia University, and also associate research scientist at the Flatiron Institute. Colin's research has been focusing on physical processes that affect the CMB photons as they travel through the cosmos, and develops new methods to separate the cosmological signals from the foreground contaminants, and uses the CMB to search for evidence of new physics. In particular, in the year of 2014, he played a key role in demonstrating that the claimed detection of the primordial gravitational waves in the CMB actually was due to the dust of contamination from the Milky Way. More recently, his focus is on the development and assessment of theoretical models that could potentially resolve the tension of the Hubble measurements. So today, Colin is going to tell us searching for new physics in the universe's oldest light. Colin, please.
All right. So first, let me thank the organizers for the invitation to give this talk. This is a somewhat unique colloquium that I'm going to tell you about some exciting new results that are going to appear on the archive tonight. I just submitted the paper a couple of hours ago, so you'll be the first people to see these results. So I'm going to talk about a few topics related to this general theme of searching for new physics in the universe's oldest light. See if I can get my mouse to show up. All right, maybe not. Well, at least the people in the room will be able to see the pointer. Okay, so I'm going to talk about a couple of papers over the last year or so with this cast of characters. I want to highlight the junior people in particular. Evan McDonough, who was a postdoc most recently at Chicago and just started a faculty job in Canada. Michael Toomey from Brown, Misha Ivanov, who's now at IS as a Hubble Fellow, Marcus Simonovich at CERN, Leander Thiel, who's a grad student at Princeton, and Yulin Guan, who's a grad student at Pittsburgh. And the work I'll talk about that's just coming out tonight is with the whole ACT collaboration. Okay, so the type of new physics that I'm going to talk about is motivated by what I'll call the Hubble situation for today. Most people have probably heard about this, but it's related to the question of how fast the universe is currently expanding. Of course, there's been coverage about this question in the popular media because some of our measurements in cosmology seem to be giving discrepant answers. So I don't want to talk too much about the global observational situation in this talk, in particular, not the low redshift situation. But let me just open with a statement that my personal view is that the observational situation remains somewhat unclear. So I have a personal little compilation of H0 measurements that I update from time to time. And yesterday I took this talk as inspiration to update it again. So the top half of the figure shows indirect inferences of H0, which are based on cosmological models cosmological measurements that assume the Lambda CDM model, our standard model, whereas the bottom half of the figure shows direct measurements at low redshifts. For example,
we're not seeing your screen. You're not sharing your screen.
It's not changing slides, or it's not sharing at all.
It's not sharing.
Huh. Well, let's try to reset it.
What you need to do is share a screen.
Click the share screen, and you need to pick the individual window or.
Yeah, okay, good.
Thank you.
Okay, perfect. Thanks for the heads up. And sorry for the various technical troubles we've had today. Okay, so these top measurements, again, are cosmological in nature and assume the Lambda CDM model. And then the bottom set of measurements are based on direct inferences by measuring, for example, distances to nearby galaxies. So famously, the most precise indirect measurement from Planck, from the Planck CMB, disagrees with the most statistically precise low redshift measurement from the Cepheid calibrated supernova 1A from the Shoes collaboration at about 4 sigma. But as you can see from this collection, there are some low redshift measurements that do agree with the cosmological inferences. For example, calibrated supernova 1A from the tip of the red giant branch, or the latest iteration of strong gravitational lensing time delay distances. So my opinion is that this is still a somewhat messy observational situation. But I think that regardless of the statement of tensions or whatnot, the situation has motivated us to think about types of new physics in cosmology that we otherwise probably would not have. And that's been something that's interested me for the last couple of years. So the basic statement that we're asking is, how can we increase the H0 value that's inferred when we fit data from the CMB in large scale structure? And it's not so easy to do this, as many of the other participants in this week's workshop can tell you. So there's two general approaches one might take. The first one is to modify the cosmological model at late times, redshifts near 0. But such modifications are highly constrained by the relative expansion history data that we have, for example, distances from baryon acoustic oscillation measurements, or type 1a supernova distances. And here I use the word relative to mean that we're looking at the expansion history, in a relative sense between different redshifts, but not in an absolutely calibrated sense. Okay, so there's a nice paper from Lloyd Dox and Marius Malea that kind of ran through a bunch of different ways to think about introducing new physics that can increase the inferred value of H0. And this sentence from their abstract summarizes, I think, what a lot of us have concluded, which is that the set of new physics solutions that increase the expansion rate in the decade of scale factor expansion just prior to recombination are the least unlikely to be successful. So not the most likely, but the least unlikely, reflecting the difficulty of this problem. So I certainly agree with this statement. So this is exciting because a generic consequence of this scenario is that there would be new signals in the cosmic microwave background. So we can go out and look for them, as this Atacama Llama is doing here, with a map of E-mode fluctuations behind him. All right, so that just sets the stage. So here's what I'm going to talk about. So I'm going to mostly focus on measurements from the Atacama Cosmology Telescope in this particular talk, but also in combination with other experiments. So we'll start out talking about that. There'll be an aside for some of the local experts who are here at the workshop about Einstein-Boltzmann codes and their accuracy. Then I'll talk about this early dark energy scenario with new results that are appearing tonight on the archive from ACT. Then if time permits, I'll talk about a second approach based on primordial magnetic fields. And then I'll conclude looking ahead to imminent data from ACT, as well as our successor experiment, the Simons Observatory. Okay, so first let's start out with ACT. So here's a picture of the ground screen around our telescope. The telescope's actually inside there. So ACT is a multi-frequency CMB survey that's been observing from the Atacama Desert in Chile since 2008. And you can tell this is a great place to do CMB measurements. Just look up at the sky. So we've been observing for 13 years now with some gaps for upgrades. And we've covered in our most recent observing seasons about half the sky. So this is a very powerful CMB data set. So here's a picture of the actual telescope inside of the ground screen. Maybe partially held together by duct tape now, but it's still working. Here's a picture of the collaboration from our last in-person meeting before the pandemic. There's of order 100 people or so currently working within the ACT collaboration. So everything I'm going to talk about here is derived from our data release 4, which came out last year. The two key papers were Iola et al. And Choi et al., which presented the maps, the power spectra, many null tests, and then derived cosmological parameters within Lambda CDM and some simple extensions. But there's a whole host of other interesting things that you might want to take a look at from this data release. In particular, I worked a lot on these component separated maps. There's also gravitational lensing maps, a catalog of 4,000 SE clusters, and lots of other interesting things. So all this is online, and I encourage you to take a look at it. Okay, so let me walk you through our main cosmological analysis from last year and the data that underlied it. So the data release 4 data set consisted of data collected between 2013 and 2016, which for the aficionados was mostly the ACT pole era, our 2nd generation receiver, but includes 1 season from the 3rd generation receiver, advanced ACT. As you can see, we cover a wide swath of the sky, about 17,000 square degrees. Some regions here are surveyed to much greater depths than others. This deep 5-6 region is the deepest one, and then this Boss North region is also pretty deep. So it's sort of a wedding cake survey strategy. The cosmological analysis that I'll discuss uses power spectrum measurements from the deepest 5,400 square degrees of these maps. Okay, so why are we still measuring the CMB? If you don't work in cosmology, you might say, well, I heard about Planck and I thought that was the end of the story. We can actually improve measurements significantly over Planck with experiments like ACT and SBT, in particular on small scales. So this is a small slice of a Planck map at 150 gigahertz. And here's what it looks like if you fold in ACT data as well. This is from work by Sigurd Ness on behalf of ACT. So you can see that the picture just snaps into focus very dramatically. And in particular, we can also resolve interesting small scale features like point sources from radio and infrared emission, as well as clusters in the shadows that are cast in the CMB by the thermal Sunyaev-Zeldovich effect. So there's still a lot of information to unpack on small scales. All right, so this talk is meant to be targeted not only at the experts. So let me just remind you that of how we actually infer cosmological parameters from data like this. So under the hypothesis that the CMB is a Gaussian random field, all of the information is contained in the angular power spectrum of fluctuations, which we measure in both temperature and polarization. So this is a cartoon produced by the WMAP team some time ago that shows the actual CMB power spectrum in comparison to a flat featureless power spectrum. And you can think of power spectrum as telling us about the amplitude of fluctuations on different scales in the map. So if we look at the first peak in the actual power spectrum, there's much more fluctuation power on that scale than there would be in this comparison flat angular power spectrum. And when we look at these plots, we're looking in harmonic space. So large scales are on the left and small scales are on the right. So the data is represented in this fashion. And then one of the big achievements of the past couple of decades of cosmology is that we've worked out how to compute the theoretical predictions in cosmological perturbation theory for these curves from first principles. And they turn out to match the data very precisely. So we compute these theory curves using Einstein-Boltzmann codes like Hammond class, and then compare them to our power spectrum measurements. So that's the basic pipeline. All right, so to give you some intuition about what we're measuring, here are some small slices of the ACT DR4 maps, just 150 square degrees here. So this is a temperature map on top and an E-mode polarization map on the bottom. So the temperature, very roughly, you can think of as telling us about the density of the primordial plasma at times around recombination, and the polarization, the E-mode polarization, tells us about the velocity of the primordial plasma at that time. Okay, so fast forwarding through many years of hard work by many people, here's the baseline foreground marginalized CMB power spectrum measured by ACT. If you want to talk about the foregrounds, I'd be very happy to do that afterwards. But I'm going to fast forward through that for here. So up top, we have the temperature power spectrum, and we have the E-mode power spectrum in the middle. These are lensing B modes here, not primordial gravitational waves, and then the TE cross correlation down here. So one thing you might immediately pick out is that we don't measure the TT power spectrum at the largest angular scales, and that's because of challenges due to atmospheric noise in measurements from the ground. So it's important for us to combine with other data sets that probe these complementary large scales that we don't get with ACT, in particular in temperature. So that was ACT DR4. Here's what this plot looks like with a compilation of other recent measurements. I think this is just only missing the latest SBT 3G measurements, but we do have SBT pole on here. So you can see that there's a beautiful, consistent picture. We've measured the temperature, the E-modes, and the TE cross power spectrum over a very wide range of angular scales. And a simple theoretical model, in this case, this is Lambda CDM, fits these data at very high accuracy. Okay, so that's the qualitative picture, but of course, this talk is going to be about the details of what we can learn from these measurements. So first, let's start out the review of Lambda CDM. So again, for the non-experts, there's 6 parameters that we're interested in here: the amount of baryonic or atomic matter in the universe, the amount of cold dark matter, the angular acoustic scale, which connects directly onto H naught. Two parameters that describe the properties of the primordial density perturbations, their amplitude and their scale dependence, and then essentially a nuisance parameter, the optical depth generated by reionization. In addition to Hubble, another important derived parameter is the amplitude of fluctuations at redshift 0, which is called sigma 8. So a first thing that one is interested in with ACT is that we can think of this as a completely independent check of the results from WMAP and Planck with totally different systematics. They're going to see a series of posterior plots here. You don't need to try to look at all of these, but should sort of just compare the different colors and verify that indeed they either look consistent in the sense that they tend to overlap, or as maybe we'll see later, they aren't always consistent. So WMAP here is in yellow, Planck is in purple, and ACT is in light blue. And indeed, ACT is consistent with WMAP and Planck within the Lambda CDM parameter space shown here. In terms of the goodness of fit, Lambda CDM does fit the ACT data well. The PT is on the order of 10%. One thing I do want to highlight is that the assessment of the consistency between these data sets has evolved slightly in this latest paper, which is appearing tonight. And I'll talk about the reason for that in just a minute. The agreement has actually improved a bit compared to what we had in Iola et al. So immediately one can then take these results to combine ACT and WMAP, again with this complementarity, because ACT doesn't measure the largest angular scales in temperature, to form a data set that has statistical constraining power approaching that of Planck, not quite as good as Planck, but it's totally independent of Planck in terms of systematics. So that's what we did. That's what's shown here. So the purple points here, sorry, the purple curves are ACT plus WMAP. Planck is in light blue, and then ACT plus Planck is in dark blue, although that's mostly dominated by Planck. But what's important to see here is that ACT, the combination of ACT and WMAP is in excellent agreement with Planck. So zooming in, for example, on the Hubble constant, which is obviously a parameter of interest, you can see that these posteriors agree very nicely. And we infer these values shown here, about 68 kilometers per second per megaparsec, with an error bar that's, from ACT plus WMAP, about a factor 2 larger than that from Planck. So we did a lot of checks to verify that these results were stable to a wide range of variations in the analysis, varying the L range that's used, varying TT versus TE versus EE, different frequency channels to look at potential impact of systematics, and also slicing the data up into different regions on the sky. And everything is very consistent. There is one minor exception, which escaped attention in last year's papers, but they came across this winter, which is actually a theoretical issue and not an observational issue. So as I mentioned, we use these Einstein-Boltzmann codes, CAM and class, to compute the theoretical predictions in cosmology. These codes come with some default accuracy settings, and it's been standard, I think, for many years to just run them at those settings. But it turns out those are not quite sufficient for the analysis of ACT-DR4. And in fact, they're totally insufficient for next generation experiments. So it turns out that in particular, the impact of CMB lensing needs to be calculated at higher accuracy in order to get fully converged results for ACT-DR4. So this was a fun puzzle to unpack over the winter. So what I'm showing you here is the CMB lensing potential power spectrum on the left. The run at default accuracy is shown in orange with CAM. Then if you crank up the accuracy parameters in these codes, you get the light blue curve from CAM or the dash purple curve from class, an alternative code. Now, the primary CMB, of course, is gravitationally lensed by the structures that follow this lensing potential. So this leads to a change in the predicted primary CMB power spectra as well, which is shown in the right. So this is the percent change in TT, TE, and EE. And you can see that on small scales, this turns into a non-negligible impact on the order of tens of percent. We were fortunate with ACT-DR4 that our error bars get large enough at small scales that this doesn't lead to a huge shift, but it is actually noticeable. So it turns out to shift parameters by about 1/3 of a sigma. This was mostly just fortunate coincidence that it wasn't larger. So what I'm showing you here is the original ACT results in light blue, and then the higher accuracy results with improved Boltzmann calculations in dark blue. And obviously by eye, they look totally fine. But when you look at the actual numbers, they do shift by about 1/3 of a sigma. So in particular, our derived value of the Hubble constant actually increases. So the baseline high accuracy result from ACT plus WMAP goes up to about 68 plus or minus 1.1. So it's not catastrophic by any means, but I think it was an interesting thing to uncover. And if you're interested in why this primarily affects the cold dark matter density and the spectral index, we can talk about that afterward. So in a sort of funny twist, this led to us writing a theory paper a few months ago before this actual ACT analysis came out. So this was work I did with Fiona McCarthy from Perimeter and Matt Mavachirl, who's here at the workshop, also from Perimeter. So we wrote a theory paper about this finding before I could actually say that it mattered for ACT-DR4. So what I'm showing you is one result from this paper with the two of them, where I'm looking at the fractional bias on cosmological parameters in units of sigmas as a function of the maximum multipole to which your experiment is cosmic variance limited. So more sensitive experiments move to the right on this plot. And this horizontal line denotes a 1 sigma bias. And as you can see, as you get to very sensitive experiments that probe small scales, you get large biases on parameters like H0 or the cold dark matter density or the effective number of relativistic species. So it's a good thing we noticed this, because otherwise we would have gotten wrong answers with upcoming experiments. So it's easy to fix. Just turn on higher accuracy settings in your code and then test them. And then the last thing I'll just mention is that after realizing this issue, we also realized that one needs to be careful about the modeling of CMB lensing itself in order to compute the predictions for the primary CMB power spectra at sufficient accuracy for next generation experiments. So there's a number of results about that in this paper, which I encourage you to take a look at. Okay, so here's the final summary then of ACT-DR4 cosmology in the context of Lambda CDM. So the ACT plus WMAP results are here, ACT alone is here, and then these are updates with those high accuracy Boltzmann calculations that shift things up a little bit. Then 2 local measurements, the latest shoes measurement from Reese is here, and then the TRGB results from Friedman here. So you can see that the TRGB results agree nicely with what we have from ACT. The shoes results are in tension at the 3.1 sigma level. So it's actually gone down a bit, both because shoes has come down slightly and this correction pushed ACT up slightly. So there's still something there, but it's not maybe quite as catastrophic as one would have thought. All right, so now I'm going to walk you through some ways of increasing the inferred value of H0 by introducing new physics into cosmology. So in order to talk about how these work, I'm just going to give a lightning refresher about how we actually infer H0 from CMB data. Again, this is aimed at the people who are maybe not working in this subfield. So the way that this works is that there's a standard ruler that's imprinted into maps of the CMB. So here is, again, a small cutout of actual CMB map from ACT. Actually, it's maybe ACT plus, yeah, this is ACT plus Planck. So the standard ruler is just the distance that a sound wave could propagate in the primordial plasma if it's set off at time equals 0, the Big Bang, and propagated until recombination at redshift 1100. So I've tried to draw some little cartoon rulers into this picture to give you a sense visually of the size of the angular size of this ruler on the sky. And so we, of course, measure then the angular size of the ruler, which allows us to infer the distance to the CMB. So we have a distance and a redshift, and that lets us back out the Hubble constant. However, the reason that there's something non-trivial here is that the predicted size of the ruler depends on cosmological physics prior to redshift 1100, prior to recombination. Of course, we strongly constrain this by measurements of the CMB, also BVN. But it's worth keeping in mind that if we change the model, then we can change the inferred value of H0. And that's what motivates everything that I'm going to talk about. Of course, the angular size would also depend on cosmic evolution at later times, but that's constrained by things like BAO distances, as I mentioned. Okay, so if this H0 discrepancy that we've seen is not due to systematic errors of some sort, then as I mentioned, I think many of us think that the most likely explanation, or the least unlikely to be wrong, is some sort of new physics that alters the size, the physical size of the ruler that's imprinted in the CMB. So a possibility that attracted attention early on was introducing extra radiation into the early universe. What I'm going to talk about here is a more recent idea called early dark energy. And if time permits, I'll also talk about primordial magnetic fields. But the basic idea here is that whatever this new physics is, it acts to decrease the physical size of the standard ruler. Well, of course, again, its angular size has to stay fixed because we measure that to very high precision. So that means that the distance to the CMB has to be decreased, which means that H naught has to be increased because the distance is all scale like 1 over H naught. So that's the basic qualitative idea. Okay, so let's go into early dark energy. So I'm going to talk first about some papers from last year with this crew, and then again, I'll talk about these new results from ACT that'll be on the archive tonight. Okay, so in terms of actual mathematics, here's what the idea that I just described in words looks like. So RS star here is the physical size of the sound horizon that's imprinted in the CMB. This is given by this integral of the sound speed in the primordial plasma times dt over a, where a is the scale factor integrated from the Big Bang up to the time of recombination. And you can recast this as an integral in terms of redshift, as we usually do. So the interesting things to look at here are potentially changing h of z, or in principle, maybe changing cs of z, but we're going to think primarily about h of z here. Okay, so the relevant, or really the only ingredients in the standard Lambda CDM model that enter this calculation are the physical densities of baryons, cold dark matter, and photons. We know the photon density from the Kobe-Firas measurements 30 years ago, and then the baryon and cold dark matter densities are constrained from the detailed shape of the angular power spectra. So again, we measure this angular size of the sound horizon in the CMB, which is approximately related to the inverse of the peak spacing in the power spectrum. And then the angular diameter distance to recombination is just given by the ratio of this physical sound horizon divided by the angular size of the sound horizon. That's right, yes, neutrinos. I guess this should really be the radiation density, including neutrinos. Yeah, thanks. Okay, so in Lambda CDM, that's the story, and that's how we back out H naught. Now in modified cosmologies like the EDE cosmology, there's going to be additional parameters that affect the calculation of this sound horizon. In particular, we're going to increase the value of h of z just prior to recombination. All right, so let me walk you through quickly the physical idea here underlying most of these early dark energy scenarios. So the idea is that we introduce some new scalar field. This is a very light scalar field. So initially it's frozen on its potential due to Hubble friction. So down here I've put the Klein-Gordon equation, the equation of motion for the scalar field in the expanding universe. So initially it's very light and this frictional term dominates. So it's just sitting on its potential. So then it acts as another contribution to dark energy with an effective equation of state equal to -1. Then eventually, as the Hubble parameter decreases, it'll become lower than the effective mass of the field. And at that point in the Klein-Gordon equation, we'll obtain a dynamical evolution of the field. So it rolls down its potential and then oscillates around the minimum. And the effective equation of state at late times depends on the detailed shape of this minimum. So to give you some sense of numbers, if we want this thing to stay frozen until sort of the epoch just before recombination, then the mass of the field needs to be of order 10 to the -27 electron volts. So it's an extremely light scalar, much lighter than anything in the standard model. So those are some of the important phenomenological ideas. And then the last thing, as I noted briefly, is that we need to have, so the effective equation of state at late times depends on the shape of the potential near the minimum. And we need this to be greater than 0. So that way the contribution of this EDE field to the cosmic energy budget goes away fast enough that it doesn't spoil late time cosmology. So there have been a few different potentials investigated by various workers in the field. The one that seems to be most phenomenologically successful is this axion-inspired potential here. So it looks like a 1 minus cosine of phi raised to some power n. So if n equals 1, then this is the classic axion potential. But it turns out that n equals 1 yields an equation of state at late times that is w equals 0. So this would look like an additional source of matter, which messes up late time cosmology. So phenomenologically, then we need to have n greater than or equal to 2. And from a theoretical perspective, I think that's a little bit harder to achieve, but here we're just thinking as phenomenologists. And then f, the decay constant of the axion-like potential in these models has to be close to the Planck scale, which is perhaps also of interest for model building. Okay, so we can look at this model in terms of the fractional contribution that this field makes to the cosmic energy budget as a function of redshift. So for the type of models that can potentially increase H naught and from the CMB, we have the field basically playing no role at early times, and then briefly injecting about 10% of the total cosmic energy budget between redshift 1,000 and 10,000, and then rapidly going away. So it looks like something that satisfies what Lloyd and Marius told us to look for. So the parameterization that we're going to use to describe this is this parameter FEDE, which is the maximum fractional contribution that this field makes to the total cosmic energy budget, and that occurs at some critical redshift ZC. So you have FEDE and ZC, and then the final parameter to complete the model is the initial field displacement on its potential. Turns out that there's actually a highly nonlinear relation between these effective parameters and the physical parameters that appear in this potential, and one can actually obtain somewhat different results if you analyze the model in terms of the physical parameters, but I'm not going to discuss that in more detail today. Okay, so the reason that this model, of course, is interesting is that it maintains a very good fit to CMB power spectrum data while yielding a higher H0. So here's just a couple of example calculations with Lambda CDM shown in black and this EDE model shown in dashed red, and the EDE model has a substantially higher H0. And the physics is exactly what I told you earlier. It's the decrease in the sound horizon that's responsible. It is important to properly account for the perturbations in this EDE field. If one does not do that, then you get the wrong answer when you try to fit the Planck data, for example. Okay, so that's the CMB. Of course, we have other measurements in cosmology. Here's the three-dimensional matter power spectrum P of K in the exact same models I just showed you a minute ago. So now there are some differences that can be seen even on this log scale on the left. And if you look at the ratio here on the right, you can see that there's order of 10% differences at these low redshifts over a range of scales that are well measured in current data. So that tells us that there are interesting constraints on this model to be placed from large scale structure data. Now, the differences that we see in these plots are actually not driven really by the EDE itself, but mostly by the changes in other cosmological parameters that are needed to preserve the fit to the CMB. So for example, the cold dark matter density omega CDM has to increase substantially in the EDE model compared to Lambda CDM. These are some results from Smith et al. 2019. I should note that in this particular triangle plot, the shoes data are also included in the fit. And all the other ones I'll show you in this talk, the shoes data are not included, so that we can assess the viability of this model purely in terms of indirect cosmological data. So the increase in the CDM density comes from the fact that this early dark energy slightly suppresses the growth of perturbations in the early universe. We have to compensate for that. So we crank up the amount of cold dark matter. And then there's also an increase in the scalar spectral index. And putting these two things together, you get an increase in the amplitude sigma 8 and the matter density omega m, which leads to a higher value of this S8 parameter that's measured by weak lensing surveys. Okay, so this was kind of where things stood when we started to dig into this model last year. So the first question we wanted to ask is whether there was any evidence for this EDE component in the primary CMB data alone. It turned out that people hadn't actually looked at this question yet. So we fit the Planck 2018 data just on their own without including any auxiliary data sets. So that's what I'm showing you in the triangle plots here. So Lambda CDM is in red and EDE is in blue. And again, mostly what you want to notice here is just that there's no major shifts seen. So Planck does not prefer on its own the existence of this EDE. There's a broadening of error bars because there's more parameters, there's more few parameters in this EDE model, but for example, H0 does not shift. So one can look at this in terms of the constraints on this FEDE amplitude parameter, which is shown here. So from Planck alone, you get an upper bound at 95% confidence of about 0.087. It is perhaps worth noting that the critical red shifts that would be needed to maintain the fit to Planck are in the ballpark of matter radiation equality, which I think some of us have taken as a clue for model building. But Planck on its own doesn't tell you that this component should be there. Okay, so we then proceeded to do a global analysis of all the indirect cosmological data sets, including weak lensing data from DES, HSC, and KIDS, but again, not including any low redshift distance measurements, absolute distance measurements. So we called this walking without shoes. So that's what's shown here. So again, Lambda CDM in red, EDE in blue. And again, you can see that there's no big shifts that are seen. So this whole suite of precision cosmological data does not prefer the existence of this component, and H0 remains low, so to speak. So there's a zoom in right here on the H0 posterior, where the shoes constraint on its own is up here in gray. Okay, so that was our paper from March, and just March of last year, in a couple of slides. Then in June, we tried to improve the precision even further by including this effective field theory-based likelihood for the BOSS galaxy survey data. This was work led by Misha Ivanov. So just summarizing this in one slide, this is a set of posteriors now for, again, Planck, plus this BOSS EFT likelihood, plus S8 measurements from DES, HSC, and KIDS. These are weak lensing surveys. Lambda CDM is in red, EDE in blue, and green, where green is Planck alone. So putting all these data sets together gave us a very tight upper bound on how much early dark energy was allowed in the pre-recombination universe at about 0.05, which you can see in this panel right here. And the inferred value of H naught does not really increase compared to its Lambda CDM value. And there's a 3.6 sigma difference with respect to shoes that persists. And in this case, the preference is sufficiently weak that the auxiliary parameters like ZC and theta I are really unconstrained. So this was the status, I think, from my perspective of where this model stood before we started to look at the ACT-DR4 data. So there was no evidence for this EDE component in CMB only fits or CMB plus large scale structure. We had these strong upper limits. Shoes remained in tension, even in this expanded parameter space. And one of the reasons that this tension persists is that the large scale structure data just doesn't let you move up to these higher values of FEDE, which are associated with higher H naught. And that's because they don't prefer the associated increases in the cold dark matter density and the amplitude of fluctuations. So a pithy statement that we had was that this EDE model doesn't appear to restore cosmological concordance. All right, so now let me turn to the new results from ACT that you'll see on the archive tonight. So we tried to ask a more limited question in this paper, but it turned out to be sufficiently complicated that it still took a long time to answer it. So all we really wanted to ask was how robust current constraints are on this EDE model to the choice of the CMB data set that's used in the analysis. So what do we find if we replace Planck with ACT or with ACT plus WMAP? So as I mentioned, ACT and Planck are consistent at about the 2.5 sigma level in Lambda CDM, but one can ask, what do we find in the EDE model? I want to emphasize, we do not try to assess global concordance of this model or any other model with respect to the full set of cosmological data in this analysis. We're just looking at a very limited set of data. So ACT, WMAP, Planck, BAO distances, and then Planck CMB lensing, where these latter two are really just important for breaking degeneracies that involve the matter density. Okay, so here are the results. I guess you're the first people outside of ACT to see these results. So this is a triangle plot with, again, FEDE, then the critical redshift, theta I, and then H naught and S8. And there's a couple of just comparison constraints on H naught from TRGB and shoes shown here, and then the DES Y3 constraint on S8 shown down here. So ACT alone is in red. And as you look at this top left panel, you can immediately see that unlike Planck, which is shown in green, the FEDE posterior for ACT peaks at a non-zero value at some non-negligible level of significance. This significance actually increases when we fold in a WMAP, let me say WMAP in quotes data set. So for very boring technical reason, we actually use a subset of the Planck TT data, which mimics WMAP more or less exactly in this analysis. So it's WMAP in quotes, but it's for all intents and purposes equivalent to WMAP. So this is important again because ACT doesn't measure the large scale TT modes because of our atmospheric noise. So this allows us to fill those in and get a nice data set that can be compared to Planck on its own. So what you can see if you look at the blue posterior here is that again, FEDE is peaking at a non-zero value. The numerical results are shown in this box here, and it's inconsistent at, well, it's inconsistent with zero at more than 99.7% confidence. So that is indeed somewhat discrepant with what we saw from Planck on its own. If you look at the 2D posteriors here, you can see that, for example, in this panel, they are more or less totally disjoint, Planck versus ACT plus WMAP. We can then fold in the CMB lensing and BAO data, which is shown in the orange posteriors here. This brings down the preference for the EDE a little bit, but it doesn't entirely go away. So we still see a preference for non-zero EDE at greater than 99.7% confidence. And the inferred H0 value in that joint analysis in orange is at about 71 plus 1 minus 2 kilometers per second per megaparsec. So that's shown in orange in this panel right here. So it does come down a bit compared to the high H0 that was inferred from ACT on its own in EDE, but it doesn't go the whole way back down towards Planck. Yeah. Sure. Yeah. Shoes is in gray, and then TRGB is in pink. So they slightly overlap, but you can see the pink one extends to lower H0, and that's the TRGB. Yeah. There'll be a zoom in just a couple slides. Okay, this is the same analysis, just with a more expanded triangle plot. And the only panel I want to highlight is really just this omega M panel, where you can see that the inclusion of the CMB lensing and BAO data in orange is important there to really narrow that posterior down and break some degeneracies. Okay, so that's ACT. Now, what about if instead we say, let's combine ACT plus the full Planck data set? In that case, the EDE preference goes away, and that's because the overall constraining power is still Planck dominated. So that's the orange posteriors here. So everything else was identical to what I showed you a minute ago, but the orange now is ACT plus full Planck. And you can see that because ACT prefers non-zero EDE, you do weaken the bound on FEDE in this joint analysis compared to Planck alone in green. But Planck is still sufficiently constraining that, that this joint analysis doesn't prefer EDE. Okay, so I want to just briefly walk you through where the improvement in fit comes from, because we spent many months puzzling over what's going on here. So if you look at, we're just going to look at delta chi-squared for the best fit EDE model versus the best fit Lambda CDM model to these various data sets. So first, for ACT only, the improvement in chi-squared is about minus 8.7. And as I'll show you in a second, this is dominated entirely by the EE data from ACT. So that leads to a weak 2-ish sigma preference for the EDE. Now, in the ACT plus what I call WMAP in quotes analysis, the improvement in chi-squared is more noticeable, minus 15.4. And in this case, it's dominated by the ACT TE and EE data. And I'll show you that in detail in a second. This delta chi-squared is large enough that formally the preference for this new model is at the 3.2 sigma level. So we're getting to perhaps an interesting situation. Folding in the BAO and lensing data weakens the preference a bit. The improvement drops to about minus 12.7 or 2.8 sigma. And then, as I've noted, Planck alone or ACT plus Planck are consistent with no preference for the EDE. So we're getting a somewhat different story here from Planck versus ACT plus WMAP. So digging into this a little bit more in the data, where is this coming from? So what I'm showing you here are the TT power spectra, TE and EE for the best fit Lambda CDM and EDE models. In this case, to ACT on its own with the data points shown there with fantastically small error bars. And then these are residual plots where the residuals to the EDE are in light blue and the residuals to Lambda CDM are in dark blue. So you can see that in all the panels, everything pretty much looks fine, except for a region down here in EE. So it's these lowest several multipole bins in EE that drive the preference for the early dark energy from ACT alone. And it turns out that, in fact, it's even more localized than that. It's only the multipole bins here in the wide patch subset of the ACT data. So it's highly localized in the data, which might give you some pause to think that this could be associated with a systematic effect. Here's a similar plot now where this is ACT plus what I call WMAP in quotes. So that's the yellow data points that are added in down here. And in this case, you still see this wiggle down in EE in that range. So that drives the fit partially. But then the other thing you see is this coherent difference between the best fit Lambda CDM and EDE models in the TE power spectrum. So there's this overall kind of additive difference in TE, which is also important for driving the preference. So it's a bit, I would say, less clear whether that could be associated with a systematic, but the localization of the EE certainly gives me some pause. So here's a summary of the H0 inference from ACT DR4 in these two different models now. So the Lambda CDM constraints are shown as the solid curves on this figure, and then the EDE constraints are shown as the dashed curves on this figure. So Planck alone is in red. So you can see Planck, as I've mentioned many times now, does not shift when you switch from Lambda CDM to EDE, not by much. Whereas in the ACT-based fits shown in the other colors, you get these significant, relatively significant increases. The error bars are sufficiently large that one might still say it could be just a rare statistical fluctuation that we're seeing here, but it's yeah, we're on the edge of thinking that that's acceptable. And then for comparison, again, these are the local direct measurements from the Friedman group, TRGB in pink, and then the Reese group shoes in gray. All right, so a few takeaways. So David Spergel likes this phrase, results are important if true when you have some controversial new result. So I think that this phrase applies here. It's important if true, but there's still reasons to be a bit concerned. So first, let me just mention a couple of theoretical implications and then some experimental implications. So in terms of the theory, one interesting fact in those triangle plots I showed is that the ACT data are consistent with small values of the initial field displacement on the scalar field potential. So in that case, you might be able to get away with using a monomial potential instead of this sort of strange axion potential raised to a higher power. So that might be more theoretically appealing from a model building sense. Another interesting fact is that the ACT fits prefer very low values of ZC, the critical redshift, just prior to recombination. So many of us had taken this sort of coincidence between ZC and the equality redshift of 3,500 or so at face value as some model building hint, but that may have been spurious if one sort of takes the ACT results at face value. The best fit decay constants in the scalar field potential are on the order of the Planck mass. Again, from a top-down perspective, this might be something to be concerned about, but it's what we find. And then lastly, you'll note that I didn't ever quote sort of a global consistency in sigmas between the parameters inferred in EDE from Planck versus ACT. And that's because the posteriors are so non-Gaussian that the usual metric that we use really isn't even valid. So it'd be worth thinking about applying some non-Gaussian metrics to assess that consistency. But for computational reasons, we didn't try to do that in this analysis. Okay, then in terms of the experimental and data analysis side of things, I would say for all of us in ACT, this has motivated us to think very carefully about doing a comparison of ACT and Planck at the level of the maps and the power spectrum data points. We have done some of that in a preliminary sense in the Choi et al. Paper last year, but there is now ongoing work to do this at a very high precision level. And some of the systematics that one might worry about, like a drive in particular, some of this strangeness in EE would be ground pickup, possibly polarized dust modeling. And then in TE, we're thinking about potential transfer function issues that maybe aren't fully under control. So there's a lot of hard work ongoing within ACT to nail these things down as best as we can. The Planck data, they've gone through a huge amount of scrutiny in the last decade. Now we're approaching sufficient levels of statistical precision with ACT that it's clear we need to, really nail these things down as precisely as our space-based colleagues have shown us how to do. So then the final slide I wanted to say here about EDE is just looking ahead. So if these hints that we saw at sort of the 3-ish sigma level here are true, then what's exciting is that the data that we have in the can from ACT is precise enough that will confirm this model at very high significance imminently. So again, this is TT, TE, and EE, where now the residual plots here are showing you the difference between best fit EDE models to ACT or Planck. The Planck one looks like a Planck Lambda CDM model because Planck doesn't prefer EDE, either in blue for ACT alone or in orange for ACT plus DeBIMAP. And then these are in units of the cosmic variance limited error bar with these horizontal lines showing you the 2 sigma range. So what's interesting here is that in TE and in EE, there are coherent differences amongst these models at the level of 1 or even 2 sigma across vast ranges in L. We expect to hit the cosmic variance limit over some subset of this range of L with our next data release on about 30% of the sky. So I can't tell you more about the noise levels, but one can do a calculation which shows that we could then distinguish between these theory curves at more than 20 sigma. So if this really dark energy model is really true, it's really there in nature, we'll see a whopping signal for this in the next year or 2. So it's a pretty exciting time. Of course, it's contingent on us understanding the systematics I just told you about. All right, so I have just a few minutes left. think in the interests of time, let me leave out primordial magnetic fields. If you're interested, we can talk about this afterward. So this is another approach to try to increase the H0 value that's inferred from the CMB. In contrast to what we saw with EDE, this primordial magnetic field model is actually not preferred by ACT or Planck. So perhaps not as fruitful of a way forward. So if you're interested, feel free to ask me about that afterward. In the last couple of minutes, I just want to give you a sense of the near-term outlook in terms of our data coming in from Chile. So as I mentioned, everything we talked about so far was ACT data release 4. Our next big data release will be called DR6, and that's planned for hopefully sometime next year. So the DR4 release was just data through 2016. As I mentioned, we have more than four times as much data already on disk. In fact, this number is probably higher now. And we're actually still observing in 2021. So an approximate forecast for DR6 Lambda CDM constraints indicates that we'll constrain H0 at the 0.5 kilometer per second per megaparsec level, which is as good or better than Planck. So whereas previously we had to combine with WMAP to get a data set that could be comparable-ish to Planck, with our next data release, we'll actually be as good or better than Planck just on our own from ACT. So it's a huge opportunity and a huge challenge in terms of the systematic effects. And of course, our colleagues at the South Pole are also making huge strides forward, and they will be, I would say, nearly as sensitive with the full SBT3G survey on a smaller, but driving results from a smaller sky patch survey to greater depth. Okay, then the next big project coming online in Chile is called the Simons Observatory, which I'll just briefly introduce you to here. So SO will cover, again, almost half the sky, just like Raymond's do with ACT. The noise levels will be another factor 3 lower than those from ACT, with multi-frequency capabilities on six frequency bands. And then CMBS4, for those interested, would start observing sort of at the end of this in the late 2020s. So SO is a major project that's well underway. We're actually building this hardware. A lot of it's actually already down in Chile. This is a picture of the collaboration at our last in-person meeting. We're building this at the same site where ACT is currently located. So there's ACT, the Simons Array or Polar Bear, which is up here, our colleagues' class, and then SO is being built down here. Here's an actual picture of the cryostat for the Large Aperture Telescope. So this is a 6-meter cross-Dragone telescope. It's being built in Germany. This big cryostat goes over here in this receiver cabin. We had to build a completely new architecture because the way that we've done things with ACT, there's no way to pack more detectors into the focal plane. So we had to completely redesign everything. And this will have about 30,000 transition edge sensor kilometers in it, with space to actually double that if we obtain the funds to do so. And then lastly, SO will of course also search for primordial gravitational waves, the B modes in the universe. And we have a complementary set of instruments to do that. These small aperture telescopes, which are specifically targeting the degree angular scale bump in the BB power spectrum coming from inflationary gravitational waves. And we're looking to improve current limits by let's say over an order of magnitude, and aim for a detection there. So lots of really exciting stuff happening. So let me just leave you then with some take-home messages. So hopefully I convinced you that at least within Lambda CDM, ACT and Planck are beautifully consistent, and as is WMAP. I think systematics related to driving the Planck Lambda CDM H0 are totally ruled out. Now we have obtained a somewhat different story, I would say, within the context of early dark energy. ACT does yield a somewhat higher H0 than Planck. It remains to be seen, I think, whether there's some low-level systematic that we need to unpack there. But at face value, that's what we found in EDE. In terms of the global concordance of EDE, I personally think there's still some problems there, struggles to match large-scale structured data, but it does seem like this could be a fruitful path towards thinking about models that can increase H0. I didn't have a chance to tell you about primordial magnetic fields, but those do not appear to be preferred by either ACT or Planck. And then lastly, things are looking very exciting moving forward. All of these new physics scenarios that I told you about that modify cosmological physics just prior to recombination predict clear deviations from Lambda CDM, in particular in the small scale polarization, and we're going to be looking for them imminently in our data. So stay tuned. Thank you.
Thank you very much, Colin, for this wonderful talk. I think we can open the floor for some questions. Please use the raise hand function both for those in the room and those on the Zoom. Yes, please.
Yeah. All right. Yeah. So Lloyd has asked whether there's other data sets that have EE data in the range where we see this interesting residual in ACT that drives the EDE preference. Let me just go back. Yeah, to here. Yeah. So there's both SPT3G data and the Planck EE data there is actually quite good. So in this particular range, if you take Planck on the full sky, the error bars on the EE power spectrum are a bit better, I think, than what we have with ACT DR4. Obviously, on the same sky patch, ACT is better, but on the full sky, Planck EE is a bit better. So we have been looking at some plots comparing Planck EE and SPT3G EE to the ACT EE measurements here. We don't see quite the same feature. Yeah, I'll just say that. Yeah, but it's still work in progress. So if that should change, don't hold it against me. Yeah, so we didn't, sorry, so Elena asks about if we cut out this region of the data and then redo the analysis, do we still see a preference for EDE? So we didn't run that exact calculation. Each of the MCMC analyses here takes weeks to converge. This EDE model is at least a factor 10 slower than Lambda CDM for these calculations. So we had to limit the number of things we tried to investigate. So we haven't actually looked at slicing out that data completely. I will say, if you try to do this with ACT alone, if you throw away even that amount of data, our error bars will get so large that it will become completely uninformative. Maybe in the combination of ACT with WMAP, there's still enough constraining power to say something interesting. But we are, with DR4, still in a situation where we don't quite have enough data to slice and dice it as much as you might want to. With DR6, we'll definitely be able to do that, though. So we'll be doing that exercise. Yeah.
I see a question from Albert Stebbins. Albert, please unmute yourself and ask a question.
Yes, thanks for the very interesting talk and new results. I'm sort of curious about like model selection. You didn't really pick ED out of a hat, and I'm wondering if there's any possibility that it has been chosen to look at because it might fit the CMB data better. I mean, I know it's looking to fit H0, but maybe there's some other things, and you're just looking at a model that you know in advance might slightly improve things.
Yeah, so this is a very fair point. Yeah, thanks for raising this. So indeed, so one in this case we'll be thinking about sort of look elsewhere effects. So I didn't say this in detail in the talk, but one has to be careful in this model to select the prior range for the critical redshift ZC to lie in the range where you get the associated increase in H0 that you are looking for. So from a model building perspective, if these are coming from string theory axions or whatever, you could have ZC values that range anywhere from redshift 0 to redshift 10 to the 9. But over most of that redshift range, it would have no it would not have the desired impact on the phenomenology that we want. There are complementary constraints people have derived looking for ultralight axions at low redshifts. At very high redshifts, you could have huge amounts of early dark energy of this type if ZC is a high value, because this thing would just go away before it has any dynamical impact on the CMB, for example. So you are correct that we do kind of make this a priori choice about what range of critical redshifts to look at. And so that has an impact on the FEDE posterior that one derived, which is why I didn't try to sort of fully frame the model selection perspective in terms of the FEDE posterior, but rather on the delta chi-square between the best fit models. It's a bit of a tricky situation, I think, to assess the preference for this model because of this issue. But looking at the frequentist, I'd say point estimate from the delta chi-squared does give you a sense that the EDE model does improve the fit to ACT or ACT plus WMAP by a non-negligible amount, whereas for Planck it does not.
Okay, fair enough.
Yeah, I don't see any other hands up for the moment. Maybe we can just conclude. Oh, there was one more. Arthur, please.
So Arthur has asked about the other class of potential H0 increasing models coming from modifications to cosmology at late times or low redshifts. My impression is that those models are almost all highly excluded just from the combination of BAO, well, really CMB plus BAO, because they changed the relative expansion history at low redshifts. There have been a couple of papers in the last year or so, one from Efstathiou, pointing out that the way some workers in the field have analyzed those models has not always been, say, physically valid. And if one really handles the shoes data in particular in the context of those models correctly, that they are pretty much all highly excluded. I haven't worked on them personally, so there could be some exception to that statement. Lloyd probably has thoughts on this question for sure, but my impression is that they're almost all pretty excluded.
So sorry, I was actually another question. So other than the GAO, right? So I mean, the predictions here are becoming consistent with today.
That's right. Yeah. So Lloyd asks about consistency of the best fit model, for example, here to ACT plus WMAP plus CMB lensing plus BAO compared to low redshift measurements of the amplitude of structure from weak lensing surveys, for example. And indeed, the S8 posterior is down here in the bottom right. You can see that it is in particular in orange, it is higher than the DES value, which is the gray band in the background. From ACT alone in red or ACT plus WMAP in blue, the S8 posterior actually is so broad in this model that it would be fine. But I think that's a red herring because you really need to have the BAO constraint on the omega M value in order to break degeneracies and get something meaningful here. Yeah, so this, I would say, although it looks interesting in terms of the CMB fit, I still personally feel that this doesn't quite smell right for large scale structure or weak lensing. Yeah.
So I see that the
Yeah. So Salim asks about consistency between ACT and Planck in the context of other models. Yeah, so in the Iola et al. Paper last year, we did explore the simple extensions, so things like N effective, primordial helium, neutrino mass, those are all considered in that paper. And the bounds that we derived on those simple extensions were all consistent between ACT and Planck. I think N effective was slightly low from ACT, but it was sort of like a 2-ish sigma difference. And in Lambda CDM, things are consistent at the 2 to 2.5 sigma level. I do think it's interesting that this EDE model provides an example of a case where you have two data sets that agree in Lambda CDM and seem to disagree in this EDE model. Personally, I found that surprising and interesting.
I don't see any further questions. Let's thank Colin again. Thank you very much, Colin. And thank you all. Thank you all for participation. Thank you very much.
Thanks.